How's everybody doing today? If you're out there in the virtual audience right now, why don't you go ahead and type a hello in the chat bar. Let me know you're there. I'll bet it's you, Lena. You're probably my one who's here this morning. If you are, it's good to see you. Thanks for coming today. I look forward to talking to you today about sensation and perception. Don't forget, we have webinar tonight. Let's see, what is it? Your webinar is at 6 or 7 p.m. tonight? I forget. Let me go to my schedule and see what we've got going on. So I forget it. Is it 6 o'clock tonight we're doing webinar? But don't forget, we are having webinar tonight. You can do that, or you can do the discussion board. Good morning, Grace. Good to see you. I've forgotten right off the top of my head. I can't believe this. Let me see if I can figure it out right now. Go to my schedule. When do we have webinar tonight? We have webinar at, let's see, we have webinar at 7 p.m. tonight. Yeah, 7 p.m. Sorry, I'm getting old and I'm losing my mind, Grace. Holy cow. Fantastic. So remember, you can come to webinar. We're going to be talking about visual illusions in class tonight. So we can either do, you can either come to that, or you can do the first week of the discussion board and begin the discussion board process. It's up to you, but I do hope to see you tonight at 7 o'clock. Let's go ahead and get started on chapter 5. So if you remember, we were talking about sensation and perception, and yesterday I spent the class talking about vision. So what I'm going to do today is briefly go over the other sensory processes, just to give you a general introduction regarding the other sensory processes. Remember, we were talking about, if you remember, we just to go back over and remind you from yesterday, remember, I'm going to want you to be familiar with where all of the sensory cortices are. So your olfaction and your gustatory, your taste and your smell, is in the frontal lobe. Remember, your hearing, your auditory cortex, is in the temporal lobe. Your somatosensory cortex, your sense of touch, is in your parietal lobe in the right here. And then your primary visual cortex is in your occipital lobe. And then if you remember, I also mentioned we have a sense of balance, and that is coordinated by your cerebellum. Okay, so we do have these 5 primary sensory cortex. Remember, we talked about the difference between sensation and perception. Sensation is recording the patterns of action potentials on your brain that are created by your sensory receptor cells. And then there's that second process called perception, which is where you, the human, try to make sense of what it is you are smelling or seeing or hearing or touching. Now, I do want to add one thing. These association cortices are areas that take the primary input from each of these primary sensory cortexes and put them together. Okay, so you've got a primary visual cortex that responds to responds to lines, shapes, colors, and movement. And then you have a visual association cortex, which puts those together and begins to build a larger picture of what it is that you see. And it's these association cortices that can be fooled and create the visual illusions that people experience. Okay? So for example, your association cortex visual cortex might get some, and actually you have sensory cortices, association areas that put all of your senses together. So you've actually got a cortex that puts your sense of color and your sense of hearing and your sense of touch and your sense of hearing together. So for example, we might ask the question, see me, I'm red. Hold me, I'm smooth and round. Smell me, I'm slightly sweet. Take a bite, and I'm crunchy and taste juicy. Grace, can you tell me, what is it you are experiencing if you have all of these sensory experiences? If you see something that's red, And when you touch it, it's smooth and round. And when you smell it, it smells slightly sweet. And when you bite into it, it's crunchy and juicy. What exactly are you experiencing? Can you tell me, Grace? What do you think? What do you think? I'd be curious to see if you can put it all together. You are seeing an apple. You are seeing an apple. Okay, fantastic. Cool. All right, so let's go ahead. A cherry. Ooh, ah, you're right. Is a cherry crunchy though? I guess it could be a cherry. Okay, I'll have to readjust that and make that even clearer. But that's a good guess. Cherry, apple, very good, Grace. Okay, so let's go ahead and talk about our different sensory receptors, our different senses. We're first going to talk about hearing. And hearing, remember you have photoreceptors in your eyes, rods and cones that respond to light energy in the form of photons. Well, in your ear, you have mechanoreceptors that respond to pressure differences. So whenever somebody speaks or you hear somebody talking or you hear a siren, that airwaves, waves of air are being pushed into your ear and they are collected by the pinna, the outer ear here, and they're directed into your ear. And these pressure differences created by sound waves are interpreted by your ear. Okay, so you've got this air, it comes in your ear, and it is collected by the pinna, and it is directed into your outer ear area. Now, the division between your outer ear and your inner ear is this thing called an eardrum. You've probably heard of the eardrum before, and so the air pressure causes this eardrum to vibrate. Now, inside your middle ear, you have these three very, very teeny bones. The hammer, the anvil, and the stirrup, the teeniest bones in your body, and there are three of these bones. And when the eardrum vibrates, it causes these little bones in your middle ear to vibrate, and they cause another little membrane in your ear called the oval window, which is even smaller, to begin vibrating. Now, the reason that we have the eardrum and then the oval window is the eardrum's bigger, the oval window is smaller. And what happens is the vibration of the bones magnifies the sound. The vibration of the sound waves is magnified when it goes from the larger eardrum to the inner oval window. Okay, so that's what these three bones and this second membrane do. Now, inside the oval window, you've got this thing called a cochlea. All right, and you'll see there's a picture right here in the middle. If you're looking over here in the middle, you've got this big round, sort of this long strip of thing called a cochlea, and it's actually wrapped up, and it kind of looks like a little semicircular canal. If you can see that in the first picture. And what you have in this, you have a membrane that goes down the length of this cochlea. All right, and this cochlea, this cochlea is filled with fluid, and inside this fluid is this basilar membrane, and you have these hair cells that are located all along the basilar membrane. And when your oval window vibrates, it causes the liquid in your cochlea to move, and it causes the little hair cells on your basilar membrane to move. And these hair cells are actually your auditory receptor cells. And these are the cells that transduce this wave energy into pulses of action potentials. Remember yesterday I suggested to you that transduction is the turning of physical energy from the world into patterns of electrical activity. So it's these hair cells located inside your cochlea on the basilar membrane that cause pressure energy to be transduced into patterns of action potentials, okay? And if you look at the third picture right here, what you see is that this information goes from your ear through your brainstem, it goes up through your thalamus. Remember, all senses are processed through the thalamus except for smell. and then it goes up to your primary auditory cortex, which you see in the third part of this chart right over here. And that's where your brain perceives. Remember, we talked about sensation and perception. So the vibrating of these hair cells transduces this mechanical energy into patterns of electrical activity, that sensation, and then this information is transmitted along your auditory nerve through your thalamus to your primary auditory cortex, where you begin the process of making sense of these patterns of sound waves, which we call perception. Okay? Now, so you've got these hair cells floating in this fluid. I do want to take a minute and talk a little bit about your sense of balance, because your sense of balance is also transduced inside your inner ear. So you have these three circular shaped canals called semicircular canals. You have three of them, and they're each in a different direction, and they are filled with fluid and hair cells as well. And so as your head turns to the side and up and down, this fluid runs around these three semicircular canals that are in different orientations, and it causes these hair cells to move based upon the position of your head. And this information is then transmitted down to your cerebellum and gives you a sense of balance, so that you know if you're standing upright, if you're laying down on the side, or if you're upside down. Okay? So this is so your sense of balance and your sense of hearing is transduced inside your inner ear when you have these hair cells that are moved by fluid that floats around inside your ear. Okay? Now let's talk a little bit about the qualities of sound. So the cochlea is this fluid-filled rolled up tube that contains the basilar membrane and the hair cells. This is where the qualities of sound are transduced, okay? And so the deal is, when you think about perceiving sound, we have higher pitched and lower pitched sounds. Now, the pitch of a sound is determined by the wavelength. So if you get these really small jagged wavelengths, okay, that represents what we would call the pitch of a sound. So the shorter the wavelength, the higher the pitch of sound, and the longer the wavelength, the lower the pitch of sound. Okay, and so we perceive pitch based upon the length of the sound wave. If you look down here in this picture right here of the lady playing the violin, you'll notice that some of these waves are kind of slow. There's a long distance between the trough to trough or the pitch to pitch. Those are lower frequency sound waves. And then you see some of these waves go really fast. Those are your higher pitched sounds, okay? And those are the qualities of sound that determine whether or not you're hearing a high pitch or a low pitch. Now, pitch is related to the location of the hair cells that vibrate, okay? So vibrations at the beginning of the cochlea, really near the oval window, when those waves vibrate, you get the sense of high pitch. The waves that, the vibration of the hair cells at the end of the cochlea, farthest away from the oval window, gives you the perception of low pitches. So it depends, one of the ways in which we determine pitch is which hair cells in the cochlea vibrate. The ones closer to the oval window, when they vibrate, you get a high pitch. The ones that vibrate towards the other end give you the low pitch. All right. Now, there is some evidence to suggest also that the faster the hair cells vibrate, the higher the pitch sounds. So when you're hearing lots of different tones, a low tone and a high tone, it's causing all of the different hair cells in your cochlea to vibrate. And so your brain puts those sounds together and comes up with a perception of sound. So you can hear just one low sound. You can hear a middle sound or you can hear a high sound. But sometimes when you hear a high sound and a low sound together, your brain in the auditory cortex is going to combine the high pitch and the low pitch and give you the perception of a mid-range pitch. Okay, so I do want you to know for the test that hair cells vibrate and that causes the transduction of mechanical energy into patterns of electrical activity. And I want you to know that it's the location of the hair cells in the cochlea that vibrate that creates the initial sensation of pitch. And to a certain degree, it's the speed of the vibration. Now, if you'll look down here, it also talks about loudness. Not only do we hear high pitched and low pitch, but we hear loud sounds and soft sounds, okay? Now, if you look at these waves down here in the lady playing the violin, in the top picture, you're gonna notice some of those waves go up high and go way down low, and way up high and way down low. And then you'll notice some of those waves don't go up as high and down as low, and down is low. That is called the amplitude of the wave. And higher amplitude waves are perceived as being louder, and lower amplitude waves are perceived by your brain as being softer. Okay, so it just depends how tall, how high the amplitude of the wave is, and your brain interprets that to either be a loud sound or a soft sound. Now, here's the deal. If you look at this picture right underneath me, you notice that this guy is looking at his phone and his head is turned to one side and he's got the phone over here. And so how do we determine where sound is located? Well, you've got two ears, and depending upon where the sound comes from, it's going to reach one ear before it reaches the other. Okay? Now, both of them are going to hear the same pitch, but they're going to hear them at different times. And then that information is a perceptual feeling that you develop in your sensory cortex. Remember, we talked about sensation and perception. So hearing the sounds is sort of the sensation part, but then being able to judge where the sound is a perceptive ability based upon your interpretation of when the sounds reach either of your ears. So if somebody over here, mom over here, says, hey, it's time for dinner is going to reach this ear over here before it reaches this ear over here. And your brain, over time, learns how to evaluate where sounds are coming from based upon this difference in when they reach your basilar membrane. Does that make sense, Grace? Let's talk briefly about the sense of taste. Now, taste and smell involve chemoreception. So, if you think about it, the eyes are photoreceptors. They respond to photons, packets of light energy. Your ears respond to mechanical energy, the pressure of waves coming in your ears. Your taste and your smell is your response to chemicals that float around in the environment, okay? So you have these chemicals in food. So if you think about it, there's sodium and potassium. These are salt ions. When they get on your tongue, you taste salt. When you taste, there's all kinds of different sugars, if you will. There's saccharin, there's, we have all kinds of different sugars, glucose, sucrose, etc., etc. And these sugars are perceived by your brain as being sweet. And then when we perceive acids are perceived by our taste buds as being, lime? Sour taste, okay? And so you have these taste receptors, which are receptor cells that transduce chemical stimulation into patterns of action potentials. These taste receptors are actually located in the 8,000 to 10,000 taste buds that we have in our mouth. And you have taste buds on your tongue and going down the back of your throat. Okay, and so we have these taste buds, and inside these taste buds are these little receptor cells. And when a molecule fits into the receptor cell, the proper molecule fits into the proper receptor cell, it generates an action potential. So you have taste receptors that respond to glucose and sucrose molecules, sugar molecules. You have taste receptors that fit salt molecules. You have taste receptors that fit hydrogen ions, and that gives you sour. And then you have taste receptors that respond to glutamate, which gives you what you might call that meaty, hearty, stewed kind of taste. And then there's lots of different molecules, typically poisonous molecules, that give you the sense of bitter. Now, if you look at the tongue, what you're going to notice is that these taste receptors are kind of localized in different parts of your tongue. So sweet and salty taste receptors are located on the front of your tongue. You're going to get umami and sour are going to be located on the sides of your tongue. And then on the back of your tongue, you're going to have these bitter taste receptors. And so where the chemical goes on your tongue is going, so we have these different receptors. So when you eat something, the sweet's going to activate the taste receptors in the front, the sour is going to activate the taste receptors on the side, and bitter is going to activate these taste receptors on the back of your tongue. Now this information travels along our facial nerve, again like all senses except for smell. Taste goes through the thalamus, and then it goes to the gustatory cortex, which is located in the frontal lobe, right? And so your brain puts these tastes together and comes up with a final experience of taste, all right? So we have 5 main tastes: sweet, sour, salty, bitter, and you may not have heard of umami, but umami is like that yummy meat stew taste that we experience. So if you're eating a nice plate of beef stew, you're going to get that umami taste. Now, and like I said, the process of perception is putting these tastes together to come up with a final taste of what you a final taste. I will tell you that I had to have radiation therapy on my throat a couple of years ago because I had throat cancer. And the weird thing is, the radiation therapy destroyed the nerves going from my tongue. It didn't destroy my taste buds, but it destroyed the nerves traveling underneath the bottom of my tongue going up to my brain. And it destroyed my ability to taste sweet. And so I can't taste anything that's sweet. Chocolate candy, can't taste it. Ice cream tastes like nothing to me. I have completely lost the sense of sweet. Now you might say, okay, I just lost one taste. But the weird thing, it's also messed up my ability to taste fruit. Because when you eat a fruit has sugars in it, and it also has hydrogen ions, which gives you the sour taste. So when you eat an orange, or you eat a lemon, or you eat an apple, you are getting a bit of sweet and a bit of sour. Both of those are combined in your gustatory cortex to give you the perception of a fruit. Now when I eat fruit, all I can taste is the sour and not the sweet. So fruit also tastes horrible to me because my brain is not receiving the sweet and the salt, the sweet and the sour at the same time. And so my brain's trying to interpret what an apple tastes like or what an orange tastes like, and it can't because it's not getting all the different sensory experiences that it usually uses to interpret a fruit taste. Now, I do want to talk to you. Some of you actually are what we call super tasters, and you are going to have 6 times the normal number of taste buds. If you look in your book, there's a demonstration which can help you determine that if you are a super taster. Now, how can you tell you're a super taster? Most of the time, super tasters are not going to like things with real strong flavor. So if you don't like coffee, if you don't like cabbage and collards and these really strong tasting foods, you might actually be a super taster. So I invite you to go to your book to find out if you are in fact a super taster. Okay, I hope that makes sense. Looks like we still have 3 people on the broadcast. Fantastic. Let's talk about smell. Smell is also your smell is also chemoreception. So you have these chemicals that float through the air. Chemicals that float through the air are called odorants. They're called odorants. And these odorants float into your nose, and you've got hairs in your nose, right? And these hairs kind of grab these odorants and push them into your olfactory receptors, okay? And your olfactory these odorant receptor cells give you the sense of smell. Now, these olfactory receptors are located in the mucus layer in your nose. You ever notice how your nose has always got like snot and runny stuff, and if you ever get sick, the mucus starts coming out of your nose? Well, inside you've got this mucus, and this mucus helps trap these odorants so that they can activate these olfactory receptor cells. Now, up in your up in the upper part of your nose, you have 350 different types of odorant receptors. So there are 350 different kinds of chemical molecules that can activate these different types of odorant receptors. And your sense of smell is going to be the combination of these different odorant receptors. So like I said, the fact that an odorant receptor goes up into your and activates an olfactory receptor cell is sensation. That's the transduction of a chemical molecule into an action potential. But then that information travels to your olfactory, along your olfactory nerve to your primary olfactory cortex, where these different odorants are combined to give you the perception of smell. Now, remember we were talking about association cortices? I don't know if you've ever noticed, but when you get sick and lose and your nose gets all stuffy, things start tasting really funny when you're sick. And that's because your final perception of what something tastes like and smells like is actually a combination of your sense of taste and your sense of smell. I've never done it because it sounds so gross, but I've heard if you hold your nose and take a bite of a potato, you'll perceive it to be just like a bite of an apple because it's the smell of the apple combined with the juicy, crunchy taste that gives you that final apple taste that we all love and appreciate. So we have these olfactory receptors located in the mucus layer in your nose, 350 different types of odorant receptors that transduce these odorant molecules into patterns of neural activity that are then interpreted by your olfactory cortex. Now, the olfactory bulb is the beginning of the olfactory nerve that is located right up here at the top part of your nose. And you'll see this picture right here. It kind of shows you how the olfactory bulb comes, and it has little nerves that run down into this mucus layer. The little nerves running down are your olfactory receptor cells, and they go up into your olfactory bulb, which is the beginning of the olfactory nerve. Just like we have an auditory nerve, just like we have we have our visual nerve heading to the back of our brain. We have an olfactory nerve, okay? And so this nerve carries the information, all these axons carries the information into our olfactory cortex. Okay, now, here's the deal. I guess nobody really knows, but apparently smell must have evolved before the thalamus evolved in the brain. So smell is the only sensory experience we have that does not go through the thalamus. So vision goes through the thalamus, hearing goes through the thalamus, touch goes through the thalamus. Let's see, vision, smell, hearing, your sense of touch goes through the thalamus, but hearing doesn't go through the thalamus. On the other hand, though, there is a lot of innervation of this olfactory nerve into the temporal lobe of our brain. Now, the temporal lobe of our brain is our memory center. And so most people are going to have the experience of things that things are going to remind them of memories that they've had. So I'll bet each and every one of you probably has some smell that reminds you of grandma or Thanksgiving or some family event that you had. Most of the time, because there are a lot of innervations of this olfactory nerve into your temporal lobe, most people are going to have memories evoked by the things that they smell. Okay? All right, let's talk a little bit about touch. Now, you have this thing called a primary sensory cortex in your parietal lobe. And you'll see there's a picture of it over here. And what you have on each part of your primary sensory cortex is a spot that responds to touch and pressure and pain on a different part of your body. If you look, you'll see along the cortex, there are body parts that they've drawn. So you see there's a little spot on your sensory cortex that responds to touch on your tongue. So if I touch my tongue, not only does the tongue taste stuff, but it also feels touch, right? Not only does your ear hear sounds, but you can pull on your ear and you can feel pulling on your ear, right? Not only do your eyes have photoreceptors that see light, but if I press on my eye, I can feel the pressure on my eye. And each part of your body is mapped onto this sensory cortex. Now, one of the things I want you to notice is that the amount of area that you have on your sensory cortex is determined not by the size of the body part, but by how complex that body part's function is. So if you look, you'll notice that you have just a little bit of space for your arm, which is kind of long if you think about it. But on the other hand, you have a ton of space on your somatosensory cortex from your lips. Well, that's because the arm just does a few things. It moves up and down, it goes side to side. But your lips do all kinds of things. They talk, they eat, they kiss, and they have very complex movement. So the amount of space, sensory space on your somatosensory cortex is determined by how complex the function of that body part is. Now, we have mechanoreceptors. Look, here's the deal. Of all the sensory receptors, so if you think about it, your visual receptor cells are located in your eyes. Your mechanoreceptors, your auditory receptor cells, hair cells are located only in your ear. Your olfactory receptor cells are located only in your nose. But your ability to feel touch and pain comes from all over your body. So touch, pressure, pain, and heat receptor cells are the only receptor cells that are located all over your body, all right? And so these mechanoreceptor cells are responsible for turning heat energy, touch energy, pain energy, and stretch into these sensations of that you feel in your brain. And so we have multiple types of mechanoreceptor cells located all over our body. So you have mechanoreceptor cells that give you the experience of being warm or cold. We have hair receptor cells that respond to light touch going over your skin. We have receptor cells that respond to vibrations and itch on your cells. We have fast and slow pressure, which gives you the experience of sharp pains and dull pains. And then we have stretch receptor cells that can tell you when a body part is stretched out. And that's important for standing and moving because you need to know if your arm is straight out or if it's up here close. And all of these can create the sense of touch and balance and kinesthetic sense that you have. So all of us have a kinesthetic sense. I can tell that my leg is below me. That's because my brain is giving me the sense that my leg is located below me. I can tell that my arm is now above my head. These are a form of kinesthetic sense, so I know where all my body parts are relative to my body. I can also tell if they're being burned or if they're being iced. I can also tell if it's being touched, so I can feel touch, I can feel cold, I can feel heat, and all of these different receptor cells, their job is to transduce these types of physical energy, these types of mechanical energy into patterns of action potentials. And then we have nociception. Noci means pain, so the perception of pain is called nociception. Now, if you've ever been punched or stepped on something sharp, you feel a sharp sense of pain. And that comes from what we call fast fibers. And then if you've ever just been achy and your arm's aching because you used it a lot or you walked a lot yesterday and your back is hurting, you're getting pain information from these slow fibers in your brain. So your fast fibers are thicker and myelinated, and they transmit sharp pains really quickly. If you think about it, sharp pains are potentially really damaging. So your brain wants to respond to sharp pains as quick as possible. So these fibers are thicker and unmyelinated. On the other hand, your slow fibers, which transmit the low aching pains that we feel, are thinner and unmyelinated, and action potentials don't travel as fast along these slow fibers. So sharp pains travel much quicker to your brain than slow aching sensations travel to your brain. And remember, just like all of your other senses, the information from these mechanoreceptors travels through your thalamus. So just remember, all of your senses, with the exception of smell, are transmitted through your thalamus. And we have mechanoreceptors, which respond to heat, pressure, and wave energy. We have photoreceptors that respond to photons or light energy. And then we have chemoreceptors that respond to chemicals that we taste or that we smell. Okay. Today's lecture was a little bit shorter. Hopefully you found that interesting. I just wanted to briefly give you an introduction to the other senses. Don't forget, tonight's class is at 7 p.m. and I've got some really cool demonstrations that are going to help you appreciate the differences between sensation and perception. I'm going to show you a really cool demonstration about hearing. I'm going to show you a really cool video about vision and sensory mixing. And then we're going to talk a little bit about visual illusions and discuss the difference between sensation and perception. Grace, do you have any questions? Lena, do you have any questions? Anybody in the audience, do you have any questions before I log off? I really appreciate you coming today, as always. This is going to be my last broadcast from Rijeka. I'm leaving Rijeka tomorrow morning. Oh, by the way, I will not be having live lectures next week. I've got 2 recorded lectures, one for Tuesday and one for Thursday. They are already on Blackboard, so we won't be doing live lectures next week. Instead, I have provided you with recorded lectures that you can watch regarding Chapter 6. Do y'all have any questions? If not, take care, have a great day, and I hope to see you tonight at 7 p.m. Take care. Bye.